Hello, how are you? This is a lecture on Wigner and Wishart matrices. So it's the sixth lecture from the series on free probability, but it's a bit independent, of course. And you can watch it just like this. No need to watch the other lectures. But it's the last one. It's probably the most beautiful, and it's the sixth one from the series. And actually, the series itself is the sixth one from a series called Introduction to Quantum Algebra. So this is really the very last slides and presentation, and I've been doing this for a month and a half. So I wrote 800 pages of slides and made about 20 hours of broadcast. I'm really very tired and allergic to anything that can be Beamer or Zoom. That's what I'm using here. But fortunately, this last lecture is the most beautiful one, so I don't have trouble in doing this. So let's find this presentation first. So for the other presentation, other lectures, if you're interested in everything, is on YouTube and slides at my webpage, and I also posted them on places like ResearchGate or Academia. So as the plan for today, Wigner matrices. That's the random matrices everything started with Eugene Wigner's discovery from the, was that 50s or 60s, that this matrices converge to the semicircle, very interesting. And then we'll take a look at Wishart matrices, which go back to the limiting law to Markovnikov Pasteur later than Wigner. And then we'll get into some more modern things like modifications of Wishart matrices, block transposed, and more generally block modified, which lead to a lot of interesting combinatorics and relations with the quantum algebra, with advanced quantum algebra, all these compound Poisson law and free Bessel laws appearing this way. So that's it. The first part 1 and 2 basic stuff, and 3, 4 it's more or less current research, and it's really recent from the last 10 years. So let's start. Well, random matrices, yeah, let's explain a bit. I mean, these are things that appeared already in the previous lectures, but let's go very quickly through all these materials. So random matrix is a matrix which is random. I mean, the entries are random variables. Now, of course, you can view this in 4 possible ways. So it's either Mn of L infinity of x. I mean, matrices variables there. Very useful sometimes is to put a tensor sign there. Mn of c tensor L infinity of x. It's the same thing, but in regard, it's better to do it with tensor sometimes. Now you can do it the other way around. So you can say that this is the same as L infinity of x comma Mn of c. I mean, to any point of x, you have your space x, that each point of x leaves a random matrix. Okay, so that's exactly the same thing, but some people prefer to view it in this way. I mean, is a random matrix a matrix for random entries, or just a family of usual matrices? That's depends on what you want. And now the fourth thing, so if you do it the other way around, L infinity of x comma Mn of c, you can also put a tensor there. So it's L infinity of x tensor Mn of c. So there are 4 things, and depends on the literature people use quite often, even in the same paper. I will do it in the slides here. More, yeah, at least 2 or 3 formalisms. So usually you pick one of them, either Mn of L infinity of or L infinity of Mn, and technically you always need tensors. It's better to do it with tensors. So hope this won't be very confusing. That's always the case with random matrices. There are several ways of looking at them. Now, in what regards the moments and the distribution, once again, there are as many methods as many people in this world. So here we'll use the following formalism. So the moments, definitely, these are these numbers. It's well, it's the moments with respect to the trace here, which is the integration over x, and then the normalized trace, okay, of matrices. That's why I put this 1 over n here. 1 over n usual trace is the normalized trace of matrices. So erase your t to the power k, with k being actually a colored integer because you're interested in t and t star, products between t and t star. And by definition, t to the white is t to the black is t star. So an arbitrary product between t and t star is a product with respect to a color integer, okay? So for instance, t to the k, which is here, white, black, black, white, would be t times t star times t star times t, okay? So these are definitely the moments. Of course, you can put tensor products, however, it depends on your formula. So with this definition here, that's the formula, okay? Now the distribution, once again, in the general case, there's no probability there. I mean, this is, t doesn't come into t star. So if you're interested somehow in the law of t star, this is a joint law somehow. This is a abstract non-commutative distribution. So it's just a functional non-commutative polynomials, which is obtained. I mean, you take your polynomial, you apply to t, and it's adjoint, and then you take the trace. I mean, which means, as usual, integrate over x with respect to the probability measure there, and apply the trace of normalized trace of invariant matrices. So that's what we can do. Okay, in general, you can go beyond that. It's abstract. It's like yeah, distribution. Now, of course, this definition for the moments with colored integers, t to the colored integers are exactly the monomials here. So by the linearity, the law is uniquely determined by the moments. So this is the general setting. It's a bit abstract. Now, in the self-adjoint case, most random matrices are self-adjoint, actually. So that's the law. Because t is equal to t star, you can just take usual polynomials, right? No need to bother with x star, which is equal to x anyway. So we take usual polynomials, and now by the theorem of Breeze, let's say, this comes from a probability measure on the spectrum of t. And the distribution of the polynomial is just the integral of the polynomial with respect to the law. So now we'll agree, well, this might seem a bit confusing, but that's what everyone does. So all these mu's here, we have mu, the law in general, mu restricted to polynomials, and also the measure, in the self-adjoint case, gives mu. We'll use mu for all the things and call it law. So it's somehow the idea is that in general, mu is the law as best as it can be. So in general case, that's your law. In a self-adjoint case, that's your law. It's better than this, but this is the same as the measure. So that's why we use the same mu. So this comes from, once again, there are many ways of viewing these. People in random matrices use their own way. Well, depends on which kind of random matrices. I'm also in random matrices. So this comes from spectral theory. I mean, in the self-adjoint case, I have there C star or new von Neumann algebra. You see, this is a von Neumann algebra. So if you know a bit of von Neumann algebras, whenever you see a self-adjoint operator, the algebra generated by this operator is commutative. So it's just the functions on the spectrum. So everything lives there on the spectrum. In particular, such kind of functional is given by a probability measure on the spectrum. Now we'll also need a few things about freeness, or this Voiculescu theory. So if we're given a star algebra, but quite often C star or von Neumann algebra with a trace, algebras are called independent when, well, they're independent, as you know, this is the condition. And free, basically the same thing happens, but now no longer take just products BC, with being BC and C, but alternating products. Why? Because you have freeness. I mean, these alternating products cannot be collapsed to something simpler. Things don't commute, so you have to take all of them. So as basic examples, if you take two algebras with traces, you make the tensor product. They're independent inside, as they should be, and they are free inside the free product. So this was for the algebras. Now for elements, two elements are called independent or free when the algebras degenerate. Star algebras, of course, are independent free in this sense. So you see, free probability is somehow a kind of twin C star of classical probabilities. There are two things, classical free. And this is best seen at the level of central limiting theorems. So you see the free CLT, this is the real version, this is the complex version. It's exactly the classical CLT with a few changes. So instead of idea, and assume that everything is FID, F stands for free. So the variables are self-adjoint, free, independently distributed. Then, as in the classical case, center same variance T, and then you make the same averages as in the classical case, and you get the Wigner semicircle of parameter T. That's a theorem of Voiculescu from the 80s. And proof is by linearization. I mean, in the classical case, the CLT proof is with a Fourier transform. Here I have a transform called arc transform, which does the job and linearizes the convolution. And that's how you get into the Wigner law. Now I have a complex version of this. So take, once again, random variables, but an abstract P-star from Riemann algebra with a trace, and you assume that they're no longer self-adjoint, but the real and imaginary parts are FID center same variance. Well, if you make these averages, of course, it will follow a law of type, well, a combination of gamma t with itself. I mean, it's a gamma t plus I gamma t somehow. So this is best stated in this way. It's capital gamma t. So gamma t is the law of A plus AB is k by the square root of 2, where A, B are semicircular following gamma t and free. So that's just, I mean, it's just the real theorem complexified. I mean, there's no need to prove it again, but this is interesting because it's a bit like in the classical case. The CLT have the real normal law, the complex CLT have a complex normal law. If you go to more advanced level, it's not the same thing. I mean, the normal law, the complex one, has many interesting properties that you don't see in the real case. It's the same thing here. This law, which is called Voiculescu circular law, has many tough combinatorial properties that are not, you can see them in with Wigner laws. So this is just a triviality, the second theorem, but if you go to a more advanced level, it's not trivial, especially the limiting law there. So with this, we can state now the result regarding the Wigner matrices. So a Wigner random matrix is a random matrix whose entries are IID complex normal variables, but up to the constraint that the matrix is self-adjoint. Remember, we read one self-adjoint matrices for having the distribution wanted a real measure that we want to compute and play with. So this matrices basically are IID everywhere, but up to this constraint that M should be equal to M star. So in practice, this means that the upper diagonal part is just IID, complex, and the lower diagonal part is the reflection of this. And on the diagonal itself, it's IID real, okay? So that's by definition of Wigner matrix. It's the most like random one, which is self-adjoint somehow. And first we have Wigner's theorem that each MI follows a semicircle of gamma t when it goes to infinity, the size. T is given by it's determined by the variance of the matrices. And then comes Voiculescu theorem stating that these matrices, the semicircle laws found by Wigner, are asymptotically free. And that's very interesting. And proof, for instance, by moment method. So we won't do it here. We'll have many results for random matrices. We'll prove via moment method, and we'll just prove one of them, the Martin-Pastur one. The other ones are just similar. So just wait a bit for a moment method proof. Well, you can just believe me. Now, so this is the Wigner matrices. Now the problem is what happens when you leave this self-adjoint assumption. So these are many names for them. Let's call them Gaussian matrices. So just IID complex normal entries without any constraints. So each of them follows a circular law, then goes to infinity, and these become free. So this is quite tricky because if you want to prove it, the first item doesn't follow from Wigner because you have there the real and imaginary part. You must show that they are free, so there's freeness in this result. But one follows from 1 and 2 here. So if you use both these things, you obtain the 1 here, and of course the 2 also. So see, getting back to this, I mean, these results really are together. Okay, first one is very old due to Wigner. The second one is from the late 80s due to Wigner, but they really go together. For instance, if you want to extend this to a complex case, you really need both. Even just for the, if you take a single matrix, you need both. So they come together. Okay, so that's about Wigner matrices. Of course, you can go far away with these things, but here I rather insist on Wishart matrices. So let's get now into Wishart matrices. So here we need a few preliminaries on Poisson laws. So that's the Poisson limits theorem. The free one, it's exactly like the classical one. So you take this kind of Bernoulli and you convolve it with itself, but this time with respect to the free convolution. So what happens in a classical case, if I put a usual convolution here, you get Poisson of t proof by Fourier. In the free case, which is here, the free convolution, we get the Marchenko-Pastur law of parameter t, which is this guy here, also called free Poisson because it's also free Poisson limits, and proof by R transform. Also need a version of this, the compound Poisson limiting theorem. So let's go back to the previous slide. So this measure here will modify instead of delta 1 here, we'll put an arbitrary measure nu. So best is actually instead of t delta 1 to put nu. Well, there are many conventions here. Let's use this one. And so given a compactly supported positive measure on R, not necessarily a mass 1, or mass t, let's form this thing here. It's exactly as before, but instead of t delta 1, I put nu. This limit converges, and the limit is called compound free Poisson law. That's the first part of the theorem. And the second part of the theorem says that for discrete measures, when you just take Dirac masses at Gi, coefficients Ti, then that's your formula, the limiting law. It's the law of a very explicit variable. You just take Poisson of Ti variables, which are free. Ti are the weights here of the Dirac masses. And you multiply by these Gi's when the Dirac masses leave. So that's the result. Well, proof once again, part transform or moment method, cumulants, whatever. They are transform, let's say, they're the simplest. And of course here, so once again for t delta 1, let's check. So this is the Poisson limits theorem. And here what do I get? So nu is t delta 1. So I just have one t, just one Poisson of t variable, and multiply the coefficient Zi is 1. Yep, so I get Poisson of t. Okay, so this generalizes the previous result. So we'll need all this. We also need, we'll do everything via the moment method. So what are the moments of Marchenko-Pastur? In parameter 1, where the formula simplifies, let's go back to the formula. So see when t is 1, this Dirac mass disappears, and here you have 4 minus x minus 2 squared, so lots of simplifications. And that's your formula here. It's very simple, supported on 0, 4, something like this. The moments are the Catalan numbers, which are another formula. And what these Catalan numbers are, if you go to OEIS or Wikipedia, whatever, you'll find huge pages on them. In my opinion, that's their definition. They count the non-crossing partitions of 1K. That's my favorite definition, and we'll use that actually. When you do moment method and combinatorics, that's your definition of Catalan that you need. So you don't really need the formula here, but rather the fact that the moments of Marchenko-Pastur count the partitions. So this is something. And then second thing, in the general case, well, same thing happens, but the partitions no longer contribute to the one contribution, but to the t to the number of block contribution. So how to prove it? Well, moments. Normally, you would like to say that you want to compute moments by whatever partial integration and reach to these things here, which in practice means like Stirling Bell numbers, but not really need, because this guy here, we computed last time, the R transform is quite simple to compute. So the R transform, you get somehow the moments. That's it. It's like the accumulants. Well, It's well known. So now with this, let's go to Wishart matrices. So what's a Wishart matrix? The real complex one here will be interested in complex one. Whenever I say Wishart, it's going to be complex Wishart by definition. So I take a rectangular Gaussian matrix with ID entries M01, following G1, the normal of parameter 1. And this rectangular matrix, well, it's better taking rectangular for a number of reasons. We'll see later. If I make GG star, now it becomes square, right? It's of size nn. And I've just normalized by 1 over m. So that's a Wishart matrix of parameters nm. Once again, it's an n by n matrix, but it comes from an n times m Gaussian matrix. And the result of Marchev-Pastur is that in this limit, so I have to make both parameters tend to infinity. But the point is that to keep the scale between them constant, which is this t here. So in this limit here, we get the Marchev-Pastur law parameter t. How is the proof? Well, the moment method, I mean, you apply the weak formula for the moments of that guy. It's only Gaussian variables, right? So let's go back here. So moments, this is self-adjoint, okay? So just need to compute moments, plain moments, no for integers or whatever. So I take a product, GG star, GG star, GG star, and then the moments, well, just integrate there. I mean, we get a huge product of Gaussian variables. I apply the weak rule, and then, well, some complicated combinatorics, but in this limiting here, you look there at which partitions contribute, and everything simplifies. You obtain the Catalan numbers as t is 1, and in general, there t version with these blocks in general. So that's the proof. Once again, we'll do a moment proof a bit later. So complete moment proof. But that's the idea. Now, let's get to some more modern things now. So one interesting thing that you can do with Wishart matrices is actually the Gaussian too, but most any kind of random matrices, but most of the work has focused on the block transpose case, on the Wishart matrix case, is to transpose blockwise or modify blocks in other ways. So let's start with the transposition. This is somehow motivated by quantum information theory, guys. They're interesting, this kind of things. So it's Guillaume Aubrin started these things, and me and Yon, Nikita, and then some others. So that's work with Nikita following Aubrin. That all explained in this few slides here. So let's take a complex Wishart matrix of parameters now dn and dm. So it's a composed number. Instead of nm capital, it's dn dm, which means a random matrix of this type, j being Gaussian, dn times dm. So that's the normalization factor here. Now, this is a matrix dn times dm, so I can right away regard it as a tensor product, right? It lives in m dn of c. So I can regard it like this. And I can apply the transposition, let's say, on the blocks here, the n blocks. Okay, I transpose on the blocks. So I'll denote it by W prime and call it block transposed Wishart matrix. So what's the limiting law now? So there's a long story here, but well, here is the result. Story later. So I take exactly this thing, and now I will keep nm fixed, and d goes to infinity. And well, the rescaling follows a free difference of free Poisson laws, these being the parameters. But why we mind this? Well, the sign here is exactly the free additive convolution, but to the minus sign, if you want. So this means that this is the law of a minus b, if you want, with a being a free Poisson of s, b being free Poisson of t, and a being free. That's it. And s and t depend only on m and n. These are the two things. So you can see this is quite interesting. I mean, this is a compound free Poisson law, right? This kind of sum differences, whatever, any kind of linear combination of of Poisson laws is a compound free Poisson law. Maybe let's go back to that slide. So you see compounds. Poisson are exactly, you can get exactly this measures here. It's an arbitrary combination of Poisson of Ti variables, and Ti vary and the coefficients can vary too. So these are exactly the compound Poisson laws in the discrete case where nu is discrete. So yeah, it's if you want these compound Poisson laws, you can think of them somehow. The order of complexity is the length. So if you just have one variable here, that's Poisson, right, of T. Now, if you have things of length 2, I mean linear combinations, these are exactly what we find here. Now, since the parameters, of course, this can take any values when m and n vary. So you basically get any kind of length to compound Poisson law. So that's very interesting. I mean, come on, cat. A cat here. It's hungry. So this can basically be any kind of compound Poisson laws of length too. So that's very interesting. It's a modeling result. From an abstract point of view, it's a modeling result for this compound Poisson laws of length too. We'll see later that you can do it at any length. But once again, these things, so that's more for fun. I mean, these things really are interesting in quantum information theory, so that's the main motivation for, we'll get back to that later. So, let's see the proof here. That's a proof now, which is a bit more complete. Of course, it takes like 5 pages of computation. So I'll just give you the ideas, keeping the combinatorics and sort of combinatorics there. So what you want to do is to compute the asymptotic moments, of course. And let's go back to the definition of the matrix. Well, it's basically a Wishart matrix here, you transpose. So now when you compute moments, so basically take the same thing, I mean, GG star, but with some transpose is there. And the moments, once again, it's a huge combination of ID variables. So you apply Vic, you get into combinatorics right away once you apply the expectation. So apply the expectation Vic and you get into combinatorics. And as usual, combinatorics simplifies in larger limits, which is actually the large D limit here, into our normalizations. And what you get is something like this. So usually when you do such things, you always get partitions which contributes. That's always the same thing, no matter what you do in random matrices of Wigner integration or any kind of quantum groups, whatever. So factors, it's always in these formulas, meander determinants, many things. So it's always partitions which contribute with certain contributions. And the contributions here are quite tricky. I mean, for Marchi compositor, you get T to the number of blocks, right? That's the moment of free Poisson of T. Here we get also M to the number of blocks, but also you get this weird term here. It's M to the number of blocks having given size. It becomes more complicated. Blocks of given size. Now, well, with this, so if you have the moments, let's go back. So that's a asymptotic moment. Now we must compute the R transform. That's what we want. So let's just compute the moment generating function first. So we have to compute the moment generating function of this beast here. Then we do some combinatorics, and finally you find this equation. Okay, it's always the idea to find the equation for these things. You cannot really compute it explicitly, but you have this equation, which is very simple. So if your parameters are here, M and N, D has disappeared. That's the big D, the big D limit. So I get this. So now we're almost done. I mean, it's enough to pass from the moment generating function to the R transform, which is very simple. I mean, you just rescale F has to get Cauchy, and then you invert Cauchy and subtract xi minus 1. That's the R transform. So once again, we don't want to compute explicitly the R transform, but rather to find an equation satisfied by 8. And that's it. If you do all this manipulation I was talking about, Gaussian and then invert, subtract. And actually, well, good news is that actually we have a solution for this. That's it. It's as simple as this. So you would like to say that, well, we can stop here. I mean, what's the measure having this R transform? And, well, this can be written as this, right? That's what you do with fractions usually. Use the roots of the polynomial here. And now each of these guys here, it's something extremely simple. It's R transform of Poisson law. We're done. So you see, that's the R transform of this, that's the R transform of this. And now equal plus for an R transform means that the things are free. Minus is the same thing, it's a free difference. So that is your proof. Now this, you can do many interesting things, and these guys like Nikita and the others are especially interested in when this this measure is positive. It's yeah, well, that's what they do. And the spectral measure, you see, this is no longer positive, the matrix. I mean, the Wishart is positive, but if you mess up the blocks like this with transposition, of course it stays self-adjoint. The spectral measure is real, but it's no longer positive. And the interesting question is to see when it's positive. Well, for this, I mean, you can forget about Wishart and everything. I mean, just take this measure here. It's a question in free probability now. Take a difference of free Poisson laws. What can you say about supports and atoms? So first thing is that it has an atom at 0, at most one at 0. That's also you can prove this directly, but it's also part of very general things like Berkovich and Voiculescu spend a lot of time in investigating such things when free convolutions produce atoms and things like that. Belinsky also. So this is this one item here is just an illustration for things in free probability. You can you have a lot of powerful results of this type. And then the supports, once again, yeah, I mean, it's basically a Berkovich, Belinsky, Voiculescu. These are the guys who did these things. And you can precisely say when it has positive support. So very good. That's so what do we have? We have the Marchenko-Pastur theorem regarding Wishart, leading to free Poisson laws or Marchenko-Pastur laws. And now this block transposition things, which leads to compound Poisson laws, flanks 2 if you want. So the problem is, can we unify all this and extend? And the answer is yes. Yeah, that's another piece of work I did with Yon Nikita. And so it's a second paper that we wrote on the subject. The first paper is this, the one that we just talked about. And the second one is with general block modifications. So let's take as before a complex Wishart matrix of parameters dn dm. I regard it once again, so it's a dn times dm matrix, a square matrix. So I regard it like this as being part of the tensor product. And now, remember for transposing, we're always transposing at right. That was our convention. That left d was going to infinity. So here at right, I'll just apply any linear transformation. Can be the identity. In this case, I just get the Wishart matrix itself. Can be the transposition. This way I'll get the blocks transpose matrices, but can be many other things. So it's have a lot of freedom here. And we obtain a matrix of the units with the tilde called block modified Wishart matrix. Now you can try to compute the law of this, and well, the combinatorics gets quite serious. So cannot really compare it in general, but here's the result. So on the suitable somewhat planar assumption of phi, I have a formula like this. So let's go from the beginnings once again. We're doing what we're doing before. That's the block modified matrix. But in order to express the result, everything will depend on phi, right? And phi itself is a linear map from Mn to Mn. It's not that a familiar object. It's better to say that phi comes from a matrix like this. right? I mean, phi ultimately it's a matrix, right? I mean, it's something between finite vector spaces, so it's a matrix. And let's call lambda this matrix, okay? It has the correct size. I mean, it depends on the isomorphism that you choose there between these guys and these guys. But let's not go into technicalities. So that comes from a matrix, right? It's a matrix. Let's call lambda the matrix. And the formula is like this. So this modified matrix, suitably normalized, follows a compound free Poisson law, and maybe free multiplicative convolution with something. And what's the things here? What are the things here? So M and R, of course, are parameters from here. So we share D and the M. D goes to infinity, I remind you. And what else? D is phi of 1. So there are actually two cases. When phi is unital, everything simplifies here. This is the formula in a very general one. So yeah, let's first discuss this, and then we'll see what happens when phi is unital, everything simplifies. So in general, phi is not unital, so you have to take phi of 1, you denote it D. And then nu here, the term here is the law of D. I mean, it's the distribution of eigenvalues. That's the usual matrix now, square matrix, so it's something discrete. And the rho is the law of this big matrix here, producing phi. So that's a formula. Now, in the case where phi is unital, which is actually covers a lot of things like the identity. For the moment, we're interested in the identity that covers Marchenko-Pastur, and also the transposition. So these are both unital. So in the unital case, which is actually the central case, these ones, so you don't have this extra term here. Okay, it's a plain modified compound free Poisson law. And with the remark that this can be anything. I mean, MNR constant, so rho is the law of lambda. If you take any lambda here, this can be any measure, right? So you get all the compound free Poisson laws. Very interesting. And there's some suitable planar assumptions that I won't get into. I mean, these kind of things you can represent it a bit as Von Jones does tensor planar algebra. And, they have somehow to come from diagrams. That's the idea. So instead of getting into that, which is technical, let's see a few examples. So, well, if I take the identity, we get Marchenko-Pastur, of course. That's exactly Marchenko-Pastur here. If we just do the block transposition, we get the result we had before, right? So we get exactly these things. I mean, these are compound free Poisson laws. So we compute what's here. For Marchenko-Pastur, you just get a Dirac. Here you get a combination of Dirac, so you get this. Now, two more interesting cases, which are due to Collins and Nikita in their work before quantum channels, all that series of papers 1 to 3, is regarding compressions with respect to the trace. And you trace the second component, tensor component. Or, so here you get, once again, it's a bit like for Marchenko-Pastur. Or you can also, another interesting operation is take your matrix and to keep the diagonal and kill everything else. It's not a trace thing, it's operatory or somehow operation. So here also, again, we get some so this is very interesting. I mean, these four things are exactly Marchenko-Pastur and block transposed following Guillaume Aubrin and me and Nikita. And then discrete compressed and diagonally compressed matrices, Collins and Nikita. So very interesting. Now, there are, of course, many generalizations of all this. So this is just the beginning of something that was how many, 7, 8 years ago. So there's been a lot of work in more general settings and solving some problems that I had left with Jan, Barismendi, Nikita, and Vargas. On my side, I did also some work. I told him that this these things work under some planar assumptions. These planar assumptions, more or less, well, if you agree to not to be that general, correspond to the notion of easiness somehow. That I introduced with Roland, following work with Julia and Benoit and many others. So I looked a bit into super easiness. That's the more modern version of easiness now. And a lot of very interesting results, and they're super easily modified Wishart matrices are very interesting things. And also work by Mingo Popa on this block modifications of marginal matrices. Also Fukuda Sniadi, very interesting work in connection with the Mander determinants and things like that. So this is still going on. I mean, it's very interesting, and I think in the end, it's well, you have this Generalizations thing, and somehow I think this is something much more concrete on exactly the same subject. I mean, it's free probability planar algebra of factors, and I don't remember what's the forcing. And in addition, we have one groups here, of course. So it's about quantum reflection groups and this kind of correspondence between all these areas. But there's still, I mean, what comes out for this from these forcing still needs almost to be understood and unified. So we're not ready yet, but I think that's the main correspondence. But somehow between random matrices and planar and quantum algebra of all kinds. Now, some further results which are very interesting too, and we couldn't no time to talk about them. About taking products of Gaussian matrices of longer lengths instead of just Wishart GG star to take several guys like this, and then moments and all that laws. Once again, you get a few Poisson laws, very interesting things. So that's Ian Bailey, Captain Collins, the free law papers, and many related papers afterwards. So that was it. So yeah, to conclusions in regard with Wigner, well, that was a tiny little interaction I did, but whereas remember, the result even about a single Wigner matrix is Wigner plus Wigner. We need both. And Wishart, yeah, this is definitely advanced quantum algebra, number of modifications. So this is still waiting to be better understood. So thank you very much for the attention, and hope that you like it. Slides, everything are on my webpage, ResearchGate Academia, and also we have some other introduction to other things. So this was free probability. We have also operator algebra, quantum groups, subfactors, and NMR matrices. So that's it. 100 pages of slides and 20 hours of broadcast. And now I'll just go to take some holidays. So see you soon, guys. I hope. Bye bye.